This program is brought to you by Stanford University. Please visit us at stanford.edu.
Let's just review what happens if we have some quantum mechanical problem involving some discrete variable that could take on some values, a finite number of values from 1 to n or something like that. Little n could be a discrete variable going from 1, 2, 3, 4, and so forth up to some number, something that we can measure. And if we measure it, we'll get a number, and that number will have a probability. The probability, let's call P of n. Standard rule, the sum over the probabilities should add up to 1. Total probability should add up to 1. And so always sum of probabilities should add up to 1. That's one rule. Another rule related to it, not completely disconnected, is that probabilities are governed by amplitudes. Amplitudes are related to the inner product of state vectors with other state vectors. Let's just write down one or two simple rules. First of all, the basis vectors that are associated with n, let's call them m and n, can be taken to form an orthonormal basis. That means each of the vectors has length 1, and they're mutually orthogonal. And that we can summarize by writing that that's equal to delta nm, the Kronecker delta symbol, which is 1 if n is equal to m and 0 if it's not. Now, we can always think of delta nm, which looks like it's a function of two variables, two discrete variables. We can always think of it as really a function of only one discrete variable, namely n minus m. We could call it delta of n minus m with the rule that when n minus m is anything but 0, delta of n minus m is equal to 0. If n minus m is not equal to 0, and delta of n minus m is equal to 1 if n minus m is equal to 0. So in fact, delta of n minus m is a function of two variables, but it has a particular form, and it's really only a function of the difference between them. 0 if there's a difference, non-zero if there's not a difference. I just point that out as something to keep in mind. If we, if we plot the probability as a function of n, then it has its values on the integers. And so at one integer, it may be one value. Another integer, it may be another value. Another integer, and so forth and so on. And it's these heights which add up to 1. That's the picture for a discrete variable. If, like the position of a particle, if the variable that we're measuring is continuous, if it can take on any real number, for example, or take on some value over a range of real numbers, perhaps from 0 to 1, or more simply, any real number altogether, then we have to change the rules a little bit. We have to think a little bit what we're doing. It doesn't make sense to ask what's the probability that the coordinate of a particle is 3. The probability that it's exactly 3, oh boy, we're getting, oh, this is a fancy, please come and join me. I will have some. The probability that a continuous variable is equal to any exact particular number is infinitely small. A particular number is a set of measures 0, and so the probability for any particular value is 0. But what we speak about is the probability that the position, for example, is somewhere in some range of values, and we define a probability density. A probability density, let's still continue to call it P, It's a probability density as a function of x, and it's typically is a continuous function. For some reason, I don't seem to have any decent pens tonight. All right, so it's typically some continuous function. So could be something like that. Of course, it doesn't have to be a bell-shaped curve like that. It could have bumps and so forth, but a bell-shaped curve will illustrate the point. And we don't ask what's the probability that if we look for the particle, we would find it exactly at some value of x. We ask what's the probability that we would find it on an interval, on some interval between x and x plus delta x, let's say, an interval of width delta x. We define the probability density so that the probability itself is given by the integral of the probability density over the interval from x to x plus delta x. And that integral, that sum of infinitely small probabilities, but there's an infinite number of them in there, that's the probability, let's call it the total probability, to find the particle between x and x plus delta x. I'm making up notation as I go along. I may not even use it again, but that's the idea. In that case, the first equation up there, the sum over n of p of n gets replaced, and it gets replaced by, let's put it up there, it gets replaced by the integral dx of the probability density is equal to 1. So that's the first replacement we have to make. Now, what about the inner products between basis vectors? Before we talk about that, we should talk about the delta function. The delta function is a useful tool for studying analogs of these equations for continuous variables. Basically, it's the continuous version of the Kronecker delta symbol. That's what it is. It's the continuous version of the Kronecker delta symbol for variables, for a single variable x, which is continuous. Again, it can be thought of as a function of the difference of the variables. So the Dirac delta function, let's think of it as a function of two variables, x and y, but it's really a function only of the difference between them, delta of x minus y. And it's defined so that it's 0 if x is not equal to y, just like the Kronecker delta. And what is it when x is equal to y? The answer I'm not going to give because the answer is undefined. But if you want to think about it qualitatively, we draw the x-axis. Here's the point y. And think of y as a parameter now. Just think of y as fixed. This is a function of x, which varies as you vary x. And as long as x is not equal to y, it's 0. But when x hits y, it gets very large. Not 1, but very large. It's defined in such a way that the area under the delta function, under this spike, is equal to 1. Okay. The area under the spike is equal to 1. So it's defined so that the integral of delta of x minus y dx doesn't depend at all on y. It's just equal to 1. Now, is there any real function which does that? No. No honest-to-goodness, mathematically well-defined function can be 0 everywheres except at one point. That's okay. It can be 0 everywheres except at one point, but have an area which is equal to 1. If it has an area which is equal to 1, well, it must be infinitely high. But we can approximate it, or we can think of it as the limit of a sequence of approximations of functions which have a width, let's call it epsilon, and a height 1 over epsilon. Now, a mathematician would never accept this as the actual definition. He would say the limit doesn't exist. The limit just doesn't exist. Okay? What a mathematician would say is a little bit different. He would say the delta function is defined in the following way. It's not really a function. It's an operation which you do to functions. What do you do to functions with a delta function? You integrate it, delta of x minus y, with functions of x. In other words, whenever you see the delta function, it's something to be integrated with a function of x. Again, think of y as just a parameter. Y could be 0, in which case it would just be the integral of delta of x f of x, or y could be 1, in which case it would be delta of x minus 1 times f of x, and so forth. The delta function is defined in a particular way so that this is equal to something particular. But in order to, let's use this intuitive picture of the delta function to motivate what the answer to this integral is. This is integral dx. Right. First of all, the answer can only depend on f at x equals y. It cannot depend on f anywhere except x equal y, because the function that it's being folded in with vanishes everywhere except at x equals y. So here's a way to think about it. Supposing this point is the point y. We have some function f of x, and the value of the function away from this point is quite irrelevant to the integral, because when we multiply f of x by the delta function is 0 on both sides here, and only the value of the function in this narrow interval can be important. Now, assume that the function in this narrow interval is continuous, and so it doesn't vary very much. In fact, it varies negligibly over the tiny range epsilon. And as epsilon goes to 0, the function will vary less and less over the range epsilon. And so if that's the case, we might as well just evaluate f of x at the point y. We won't be making a mistake in the integral, because the integral is only sensitive to f at the point y. So this must be equal then to the integral, well, let's just do it in steps, delta of x minus y, f of y dx. But an integral over x, we can take f of y on the outside. Let's just take it on the outside, since it doesn't depend on x at all. It just becomes f of y. And now we use the fact, or the assumption, that the integral of delta of x minus y dx is just equal to 1. And the result is, of course, just the rule. This is the rule now which defines the delta function. It is not really a function. It's an operation that you do on a function. But whatever that operation is, it always gives just f at the point y. That's basically its definition from a mathematical point of view. An operation that you do on a function that gives the value of the function at the point y. I don't find that terribly satisfying. I find it much more satisfying to intuitively think of it as a very high, narrow function with area 1, with total area 1. Anyway, that's the delta function. Now, let's come back to the particle on a line and ask, what's the analog of the inner product of the nth state vector with the mth state vector? Now n and m are replaced by the position of a particle. And so the natural question is, if the state vectors of the system are spanned, that means if there's a basis of state vectors labeled with the coordinate position x, and x is a continuous variable, then we can ask, what is the inner product between x and y? The answer is they're orthogonal if x is not equal to y. That's the basic rule that if two configurations are measurably different, then the inner product should be 0. It's the analog of delta mn equals 0 if n is not equal to m. But if x is equal to y, it shouldn't be 0. The natural analog is to set it equal to delta of x minus y. Now notice that means that the norm of the vector, x itself, is not really defined. It's really the delta function at the origin. It's the delta function at the point x equals y, and so it's infinitely high. In fact, we never actually wind up using this quantity. We always wind up using it in this form, as you'll see. I'll give you some examples. But that's what replaces the inner product structure that's there for discrete spaces, for spaces with a discrete basis of vectors. All right, now let's go back and discuss the rules of probability. We don't need this anymore. Let's go back and discuss the rules of probability in quantum mechanics and how they're related to these abstract definitions. First, in the discrete space. In the discrete space, the probability in a particular state, if we have a particular state that's been prepared, the probability, P-R-O-B, probability. The probability that a measurement will yield the value n is given by, if psi is the state of the system, and we're going to talk about preparing states, making them, and so forth, but for the moment, psi is the state of the system. It's a vector in the vector space. Its inner product with the discrete state n is called the probability amplitude for the state n, but it is not the probability. We have to take its absolute value and square it. Another way of writing it is that it's psi n times its own complex conjugate, which can be written as psi n psi, not summed. No sum over n. That's the probability to detect, if you like, the value n for the observable that's labeled by n. What's the natural analog of that? The natural analog for continuous systems is that the probability density, let's call it P of x now, or let's call it P of y. Y does not represent a different coordinate from x. They just represent two values. X and y represent two values of the same variable. Here's the line that the particle is moving on. Let's call this point x, and let's call this point y. It's not the x and y axis. It's all the horizontal axis, and this corresponds to two distinct points. The probability that we find the particle at y in a given state. Now, how is a state described? It's described in terms of a function of x. But let's just write it. It's given by the inner product of the state vector of the system with the state in which the particle is known to be at y. Sorry, that's not this probability. That's the thing which you square to get the probability. This thing squared, which is also equal to psi y psi. But that now raises the question, how do we calculate the inner product of psi with y? Now, the vector space that we're dealing with is the vector space of functions of x. Each vector is described or labeled in terms of a function psi of x, a wave function. Wave functions like this, which are complex functions which depend on a single variable, form a vector space. So they form a candidate for the description of a particle. And we've already discussed the inner product in this space. The inner product in this space, let me just write it down. The inner product between two vectors, phi and psi, is just equal to the integral dx, phi star of x, psi of x, the definition of the inner product. So now we can apply it to calculating y psi. Let's just do it. It's equal to the integral dx, psi of x, and now the wave function associated with a particle known to be at y. That wave function is just delta of x minus y. A particle known to be at y, its wave function is 0 unless x is equal to y, and the delta function, it's 0 unless x is, yeah, I said it right, unless x is equal to y. So the phi vector here is just delta of x minus y. And it says the amplitude, well, it says what it says. Just the wave function, where did I write it? Over there. So this is the wave function of a particle known to be at y. Remember, think of y as a parameter and x as a variable. And this is the wave function of a particle known to be at y. 0 unless x is equal to y. Okay, we know the rule for calculating this integral. The rule for calculating this integral is just to substitute for x the value y. That's the definition of the delta function. That's just equal to psi of y. So here's what we found. We found that the probability amplitude for detecting the particle at y is nothing but the wave function psi of y. We've already said that previously, but I'm just describing it in a more formal, mathematical, rigorous way, that the amplitude to discover the particle at point y is given by the inner product of psi with y, and it just is the wave function at point y. From that, we immediately follows that the probability density is just equal to psi star of y, psi of y. All right, so that's applying the axioms to a particle moving on an axis, on a continuous axis. And the only really new thing is that we have to deal with the continuum of eigenvalues, or the continuum of possibilities, by substituting for the Kronecker delta the Dirac delta. Any questions? Yeah.
Yes, can you go back to the first statement at the top of that board there and go through it again, please?
Oh, this is one of the postulates of quantum mechanics. The probability, if we have a discrete set of possibilities, all right, a discrete set of possibilities could mean heads or tails. If it were a die, it could mean 1 through 6. If it were some other variable which could take on any of a discrete number of variables, then for each value of that variable, for each possibility, for each independent possibility, there's a state vector, a bra vector, and a ket vector labeled n. One of the postulates of quantum, one of the 4 or 5 postulates that I gave you the last time for quantum mechanics, is that the probability to detect eigenvalue n, I'll use the word eigenvalue n, or that the observable has value n, is the inner product of the state vector, whatever the state vector happens to be, with the basis vector n squared. Okay? That's just this times its complex conjugate. Psi n, that's this, and here's the complex conjugate. Okay? Okay. All right, now it's just a matter of substitution, a matter of formal substitution. Wherever you see n stick y, instead of thinking about discrete probabilities, think about probability densities, things that we will integrate in order to find probabilities. This is now the probability density. Replace probability by probability density. Replace n by y. Up till then, no difference. And then in a moment, we will discuss that. Okay, added ingredient, that the inner product structure that we postulated for the vector space of functions, particular complex functions, was just to integrate over x phi star with psi. That's another postulate, if you like, another assumption of quantum mechanics. Point is, it works, of course, and it leads to a nice set of ideas. Okay, so then we can calculate the inner product of psi with the vector representing the particle localized at y. It's just given by the integral of the wave function of the particle, psi of x, times the wave function describing a particle known to be at y, known to be localized exactly at y. That's this delta function, this high, narrow function, which is 0 everywheres except at x equals y and has area under it equal to 1. That's the delta function. That integral is just psi of y, definition of the delta function. So if we know that y of psi is, y in a product with psi is just the wave function psi of y, we can use that in here. And we see that the probability is just psi star psi. We could have begun with this. It would have been fine to begin with this and work in some other direction, but this is the basic set of rules, set of postulates for quantum mechanics that Dirac laid out, I don't know, 1930, somewhere around there. It's never been replaced by anything. It still stands today exactly the way he expressed it.
Question?
Yeah.
I don't understand the inner product being a delta function.
Well, do you understand?
The eigen, you said before that the eigenfunctions were essentially delta functions of this operator x, but you have an inner product.
Okay. Okay, good. Let's check and prove that delta of x minus y is the eigenfunction of the operator x with eigenvalue y. Is that what you're asking?
No, I don't understand. No, that's not what I'm asking. I'm asking, you have an inner product here, which I thought was just a number. You said you have a delta function.
No, the inner product is a number, but it depends on which x and which y. Well, come back to here. It's the Dirac delta function. It's the Dirac delta function.
If the thing on the right-hand side of the equal sign is a function, then so is the x is a variable on the left side, so it's...
No, but the thing on the right side is 1 if x...
It's not 1. It's infinite if x equals y. Sorry.
How can it be not the same direct? How can it be, how can you have an inner product that's
By the vectors themselves having an infinite length. By the vectors having an infinite length. Now, if you really want to do this right, and it would take us another 2 hours to do it right, what you really do is you replace the continuous line by a dense set of points, a dense set of discrete points. Okay? And instead, separated by a tiny distance a. Then, instead of labeling the particle by a position on the line, we might label it by which site it's at, which of these n sites it's at. Okay? We could then use the standard definition, delta nm. The implication of this is that the inner product of one of these with itself is just 1. Okay? What we would do to get to the vectors x is to multiply the vectors n by a numerical value which would be 1 over the square root of a. You just multiply the vectors by a large number. When a gets small, the 1 over the square root of a gets big, and you simply multiply all of the vectors. This x here means x can be identified with n. It's simply the coordinate position of the point located n units down the line. Okay? The vector x is 1 over the square root of a times n. That's the official definition, the way things are set up. But then if you take the inner product of x with y, what you'll get is delta of n minus m. All right, that's n minus m. Y here corresponds to the mth site, x corresponds to the nth site, divided by a. Okay. Well, when a gets to be a very, very small number, this inner product becomes infinite, or just very large, if you like, just very large. And that's the limit in which this becomes delta of x minus y. You can work everywhere if you like with a discrete space like this, but it's useful. This is a useful definition. The point is this is a useful definition. Let me show you something else. When you integrate p of x dx, that's not really the sum. That's not equal to the sum of p of x. It's equal to the integral. What's the relationship between the integral of a function of a smooth variable and the corresponding discrete sum? Well, the answer is that the integral is the sum times delta x. P of x times delta x, where each little delta x here, that gives you an area, the height times the width, and the integral is the limit of the sum of p of x times delta x, or just times a. So you see this little a interval gets into equations. It gets into equations. It gets into this equation in this form, and it gets into this equation in this form. This is what we're doing. This is what we're doing. Let's see. Can we do a little bit better than that? Well, I think if you trace it through, you'll find out that the definitions are completely consistent with this. And this a here is the same as this a here. So we're just taking all of the vectors and stretching them out by a distance 1 over the square root of a. If we stretch them out by a distance 1 over the square root of a, then all the inner products get to be very big. Now remember, this delta function, here, look, here's another way to think about it. What is this delta function? It's a high, narrow function. It's a high, narrow function whose width can just be taken to be a, and whose height is 1 over a. All right? Let's take that definition of the delta function. Its width is a, and its height is 1 over a. Okay? Now, here I've told you that I've stretched every vector out by 1 over the square root of a. So we can now calculate what the inner product of x with y is. It's just delta of n minus m divided by a. Right? But this is just a delta function. It's a function which is 0 everywheres, except when x is y, or when n is equal to m, and there it's of height 1 over a. So we've just stretched the vectors out for convenience, mostly for convenience. We've stretched them out by this factor 1 over square root of a, and then the inner product goes from being the Kronecker delta to being the Dirac delta. The Dirac delta differs from the Kronecker delta if we approximate the continuous situation by a very, very dense collection of points. Then the Kronecker delta and the Dirac delta simply differ by a factor of 1 over the spacing. Right? And if we put that factor of 1 over the spacing into the definition of the vectors here, then we come out to the nice formal convention that the inner product of x with y is delta of x minus y. You don't ever really have to do this. It's just a nice tool for eliminating lots of dependence on this small variable a. Okay. So that's the particle on a line, or the wave function for a particle on a line. The wave function is a probability amplitude, and it plays the same role as n psi in discrete quantum mechanics. All right, let's study another system. Let's study a system of a particle moving on a circular line. On a circular line, meaning a circle. Circular line means a circle. Here's our circle, and there's a particle on it somewheres. Now, I'm going to lay out this circle. I'm going to cut the circle up here, or someplace. No, I guess maybe I'll cut the circle down here. Cut it down here, and take the entire circumference of it and sort of lay it out on a line. Just to think of it as a line interval instead of a circle. What's the difference between a line interval? Well, let's come to it in a moment. Instead of labeling the circle with an angle, I'm going to label it with a coordinate x. Let's take the radius of the circle to be r, and the total circumference of the circle is 2 pi r. That means if I lay the circle out on a line, it goes from 0 to 2 pi r. The particle can be found anywheres on this line interval, or equivalently anywheres on this circle. So how do we represent vectors? How do we represent the space of states? The space of states is again labeled by position, but now x only goes from 0 to 2 pi r. Precisely the same setup. Eventually, we come to the idea of a wave function, psi of x, the square of which is the probability for finding the particle at different positions. We come again to the idea of a probability amplitude to find the particle at different locations, and the square of this. When I say the square, I mean the absolute value of the square. The absolute value of the square of this is the thing which represents the probability on this axis. But there's one thing we have to take into account if we really want to think about it as something on a circle. If something is on a circle, if a function is defined on a circle, then it has the property that when you go all the ways around, the function comes back to itself. If a function is defined on a line interval, that is not necessarily so. So in order to be studying a particle on a circle, we have to restrict ourselves to wave functions which are periodic, which means they come back to themselves after going from 0 to 2 pi r. Another way to say that is that the space, the vector space that we're talking about, is the space of functions psi of x which have the property that they're equal to psi of x plus 2 pi r. Consider the class of functions, the special class of functions, which when they start at 0 and get to 2 pi r, they come back to their same value. They're called periodic functions. Okay? Special class of functions. First question is, are they a vector space? The first thing you should think of to yourself is, am I following the rules of quantum mechanics? Is this a vector space? Well, if we take a function which comes back to itself and we multiply it by a constant, any complex constant, it will still be a function which comes back to itself. A periodic function, when you multiply it by a constant, is still periodic. What happens if you add two periodic functions, each of which comes back to itself after going around the circle? The sum of two periodic functions is still periodic. So the periodic functions are a vector space, an allowable vector space for studying a quantum mechanical system. That would be the basic setup for quantum mechanics on a periodic interval, or equivalently quantum mechanics on a circle. Okay, the last time we began to study momentum. So let's come back to momentum. Thus far, we've been studying position. Let's come to momentum. The position operator, as I explained to you last time, is equivalent to multiplication of a function of x by x itself. It takes any function of x and multiplies it by x. So it's an operation that you do on the vector space that multiplies it by x. I'm interested now in the momentum operator. The operator which represents momentum, we discussed it last time. Let's call it P. And we discussed it last time. It's I h bar minus times d by dx. Now what this really means is that the abstract operator, when it acts on abstract vectors, has the same action as minus I d by dx or minus I h bar d by dx when it acts on functions of x. There's a one-to-one correspondence between vectors and functions. And the things that you can do to a function are to differentiate it, multiply it by something, and so forth. So every operator corresponds to an operation that you do on a function. And this is the definition, or this is the operation that you would do to define momentum. Well, we worked out the eigenvectors of this operator. The eigenvectors were just defined by minus I h bar d by dx psi of x is equal to k. K is the eigenvalue psi of x. No, p psi of x. Momentum. Not probability here, momentum. Let's call it, it's p for momentum. What's the solution of this equation? The solution of this equation is psi of x is equal to any numerical multiple, incidentally, times e to the I p over h bar times x. Let's check that. If I differentiate with respect to x, it pulls down a factor of I p over h bar. I multiply by h bar, that gets rid of the h bar, and then I multiply by minus I, that gets rid of the I. So this operation, when it hits psi of x, if this is psi of x, let's call it psi p of x, it means the wave function associated with a particle of momentum p. The wave function associated with a particle of momentum p is e to the I p over h bar x. All right? To check that, what we do is we check that this psi of x is an eigenvector of the appropriate operator. Now, why this is called momentum is another question. As I emphasized last time, to check that this makes any sense to call it momentum, we want to understand how wave packets move. We want to understand how wave packets for heavy objects move, and we want to check that the motion of the wave packet is consistent with calling this object momentum. But for the time being, this is just a name. Momentum is just a name for the observable that goes with this operator. Here are its eigenvalues, all possible real numbers, and here are the eigenfunctions. It's traditional to put a square root. Okay, let's be careful now. We're doing particle on a circle. Let's consider the inner product of this wave function with itself. Let's normalize it. Let's normalize it. That means let's multiply it by a constant so that the integral of psi star psi dx is equal to 1. This is for momentum eigenfunctions. Psi sub p for the same eigenvalue. In other words, equivalently, let's require that the total probability for finding the particle anywheres adds up to 1. Anywheres on this circle. It's just a statement. The total probability of finding it somewheres on the circle is 1. All right, what is psi star psi? If psi is given by this, what is psi star psi? It's just 1. Psi star psi is just 1. So this says the integral of 1, but what is the integral over? The integral goes from 0 to 2 pi r. From 0 to 2 pi r of 1 is certainly not equal to 1. No, it's equal to 2 pi r. So in order to get this to come out to be 1, we have to multiply the wave function by the square root, 1 over the square root of 2 pi r. It's just a number. It's just a numerical number that happens to depend on r. And if we do that, then psi star psi is just 1 over 2 pi r. This becomes integral of 1 over 2 pi r from 0 to 2 pi r, and now it is equal to 1. This is just something to keep track of, that it's convenient to normalize these wave functions so that their norm, so their inner product with themselves is equal to 1. Doesn't play any great role in what I'm going to say, but it's nice to get the formulas right. Okay. What about the inner product between wave functions with different values of p? Say p and q. If p is not equal to q. Well, then the answer is 0, and you can check that just by knowing the properties of exponentials like this. But the reason that we know it is because the eigenvectors of Hermitian operators with different eigenvalues are always orthogonal. So this is something that you can check, that the integral of e to the I phx, e to the minus I qhx, or whatever, that's equal to 0. But that follows from the Hermitian property of the operator p, which we checked last time. We checked it last time by working out the property of being Hermitian. Okay, so now we have the wave functions for these particles, but there's something we haven't guaranteed yet. We haven't guaranteed this periodicity here. Thus far, a general wave function like this is not necessarily periodic. The space of states that we're interested in is the space of periodic wave functions. So let's ask, what is the constraint? What do we have to do to restrict ourselves only to those wave functions which come back to themselves? Well, the answer is that if we take e to the I p over h bar x, and we add to x 2 pi r, that it had better just be e to the I p over h bar x. In other words, after x makes an excursion of 2 pi r, it must come back to itself. That's the condition of periodicity. It's the condition that the wave function is really on a circle and not on a line. All right, well, this is equal to, of course, e to the I p over h bar x times e to the I p over h bar times 2 pi r, just the property of exponentials, and that has to be equal to e to the I p over h bar x. We can cancel this out, and our rule is that e to the I p over h bar times 2 pi r must be equal to 1. That's a restriction on the possible values of momentum. That's a restriction on the possible values of the eigenvalue, so that we actually are in the appropriate space of functions. If we choose p to be anything other than something which sets this equal to 1, it's not an allowable wave function because it's not periodic. It's not really on a circle. The condition that this is equal to 1 is the same as saying that p over h bar times 2 pi r has to be an integer multiple of 2 pi. E to the 2 pi n, where n is any integer, times I is equal to 1. And only if n is an integer is this equal to 1. E to the 2 pi I is equal to 1. E to the 2 pi I to the nth power is equal to 1. And so the general solution to requiring the wave functions to be periodic is that p over h bar times 2 pi r should be an integer multiple of 2 pi. We can cancel out the 2 pi. We can divide by r. R is just the radius of the circle, and we can multiply by h bar. It tells us that the allowable values that the momentum can take on are integer multiples of h bar over r. Let me clean that up. The allowable values of the momentum are integer multiples. Now I forgot what I said. Integer multiples of what? h bar over r. If we choose any other values of p in this wave function, it won't be periodic, and it will not correspond to motion on a circle. So what we learn, among other things, is although the position on the circle is a continuous variable, the momentum is a discrete variable. The momentum is a discrete variable, and it can only take on integer multiples of a certain quantity, h bar over r. Now, as the circle gets bigger and bigger, as r gets, let's plot the possible values of p. Here they are. They're discrete. N equals 0 could be over here, n equals 1, n equals 2, but the values of p are n times h bar over r. So that means the separation between different values, this is not a separation in space. It's a separation of the possible values of momentum. They're separated by amount h bar over r. As r gets bigger and bigger, if we imagine a bigger and bigger circle, which means that this line goes from 0 to some very, very large size, then the spacing between the different values of momentum gets smaller and smaller. And eventually, any value of momentum, or a very dense value, or a very dense collection of momentum become possible. So by making the circle very, very big, and tending toward the situation where it becomes an infinite line, in that limit, the momenta, the possible momenta, become anything. But if we're actually on a circle, if we're actually talking about a particle moving on a circle, then the momenta are quantized. Quantized means that they come in integer multiples of some particular value of momentum. That's always the origin of discreteness in quantum mechanics. Discreteness of various things which in classical mechanics can take on any value, and in quantum mechanics only take on discrete values, energies and things like that, always has to do with some periodicity and the wave function having to be periodic. Let's go one step further. Let me just remind you from classical mechanics, if we have a particle moving on a circle, it has an angular momentum. The angular momentum is called L. We worked it out last quarter, and it can be written in a number of ways, but one way that it can be written is the tangential component of momentum, let's just call it P. It's the component of momentum along the circle, which we've called P, times R. Angular momentum is momentum times distance, or the moment arm of the momentum. What does that say the possible values of angular momentum are? The possible values of angular momenta are R, that's this R here, times the possible values of P, which is NH bar over R. So we see before our very eyes that angular momentum is quantized in units of H bar. Incidentally, angular momentum and h bar have the same units, units of length times momentum, action it's called. Angular momentum comes in integer multiples, and it doesn't matter how big the circle is. However big the circle is, the size of the circle canceled out of this. And we found out, quite independent of the size of the circle, the angular momentum is quantized. Angular momentum always comes in discrete integer multiples of, except when it comes in half integer multiples, but that's another story for another day. Okay. Angular momentum is quantized in quantum mechanics. What happens, what should we do when the circle does get very big? The circle is a convenient starting point for studying particle on an infinite line. Just by making the circle bigger and bigger and bigger, eventually it approximates a particle on an infinite line. But as I said, in that limit, the spectrum, the collection of eigenvalues of momentum becomes denser and denser. In other words, it approaches a continuum. The discrete spectrum of momentum becomes continuous. What was the spacing between different momenta? It was h bar over r. H bar over r was the spacing between the different momenta here. And as r gets bigger, they get denser and denser. And in that limit, we start to use the continuum notation. Instead of describing vectors p, which have inner products which are Kronecker deltas, we stretch them out, and p and q represent two different momenta, and use the Dirac notation, p minus q. In the limit where the line gets so big that basically every value of the momentum is possible, in that limit we want to think of the momentum as a continuous variable and just use the notation of Dirac delta functions. We don't really do anything new. We just stretch out the vectors by 1 over the square root of this distance here, stretch them out, and replace the Kronecker delta by the Dirac delta. There's not much physics in this replacement of the Kronecker delta by the Dirac delta. It's just a convenience and a trick to be able to pretend that this is a continuous function, which it is not, of course.
As R gets tends toward infinity, would you then expect the regression back towards classical mechanics?
No, not well. In one respect, only in the respect that the possible values of momenta become anything. But that does not mean we go back to classical mechanics necessarily. In fact, we'll discuss that right now. Yeah. In the angular momentum, if I multiply p times r, p times r is angular momentum, so the spectrum of angular momenta, the r cancels out. In the spectrum of momenta, it doesn't. Yeah, good, right. Okay? Angular momenta and momenta just differ by this factor of r. And it's just definition of angular momentum, but it's a good definition of angular momentum. So the quantization of angular momentum ultimately has to do with the periodic nature of the angle variable. The angle around the origin here is clearly a periodic variable. Wave functions have to be periodic, even if you're not restricting yourself to motion on a circle, even if you can move anywhere in space, still, when you go around a closed loop here, the wave function has to come back to itself. And that's the content, that's the ultimate content of the quantization of angular momentum. That if you rotate around by 2 pi, you come back to yourself. You come back to the same thing. All right, so now I was asked the question, are we essentially doing classical mechanics when we let the interval go to infinity? No, not at all. In classical mechanics, a particle can have both a known position and a known momentum. In other words, it can be in a state, in fact, every state of a particle has both a position and a momentum with infinite precision. Position and momentum are simultaneously specifiable. Not so for a quantum mechanical particle. Specifying the position of a particle means choosing an eigenvector of its position operator. The eigenvectors of the position operator correspond to the states in which the particle has a very, very definite position. The eigenvectors of the momentum operator correspond to the states where the particle has a definite momentum. The eigenstates of position are these high, narrow functions that look like that. What about the eigenstates of momentum? They have the form e to the ipx, which means, the thing in the denominator here is not so important. they have the form of cosine p over h bar x plus I sine p over h bar x. Each one of these functions is more or less uniformly spread around the circle. If we tend to let the circle get an infinitely big radius, it means they're infinitely spread over the entire axis. Why do I say they're infinitely spread? Well, the easiest way to see it is just to take psi star times psi, the magnitude of the function. It's just 1. It doesn't vary on the circle. So each momentum state has equal probability of being anywheres on the circle. Each one of the momentum states separately has equal probability of being anywheres on the circle. Okay? Each position state is extremely well localized in space. So no wave function is simultaneously an eigenvector of position and momentum. Just can't have any for which the position and the momentum are both specified. So we're not doing classical mechanics. We're quite far from classical mechanics. But let's discuss a little bit the idea of simultaneously specifiable. Two variables are called compatible if you can specify both of them simultaneously. Position and momentum are not compatible in that sense. What is the condition that, let's say we have two observables, A and B. I think I called operators with little hats on top of them. Supposing I have two operators, A and B, which are simultaneously specifiable. What does that mean? That means that they have common eigenvectors. That means that there are eigenvectors which are eigenvectors of both of the operators simultaneously. In fact, the best possible situation for two operators being completely compatible is that if there is a complete basis of vectors, let's label it. I'm going back to the discrete case, but it doesn't matter, that there's a complete basis of vectors which are simultaneously eigenvectors of both A and B. Then each one of those eigenvectors, both A and B, can be specified and can be definite. So if we have a complete set of eigenvectors for which both A and B, we have a complete set of eigenvectors which are simultaneously eigenvectors of A and of B, then A and B are compatible, and they can both be known by simply putting the system into one of these combined eigenstates. Well, let's see what that means. That means we have a complete basis of vectors labeled from 1 to capital N, such that for every one of them, A on N is some eigenvalue. Let's call it alpha sub n times n. This just says that these vectors are all eigenvectors of A with eigenvalue alpha n. The first vector has eigenvalue alpha 1. The second one has eigenvalue alpha 2. But simultaneously, the same set of vectors, exactly the same set of vectors, are also eigenvectors of B with eigenvalue, let's say, beta n times n. The question is, what is the necessary conditions, necessary, in fact, and sufficient conditions, that two operators, A and B, have the same set of eigenvectors? So in order to motivate the conditions, let's study what happens if you multiply A times B and then act on n. What does that do? Well, we know what B does when it acts on n. It just gives us the eigenvalue beta n times n. So we can rewrite this as A times the number beta n. Now this is a number. Beta n is not an operator anymore, times n. Beta n is just a number. We can take it out, put it on the left-hand side of the operator A. And so that becomes beta n A times n. Numbers, ordinary numbers, you can push them back and forth at will. They just multiply the vector n by 2, And using the linearity of A, we can easily just move beta to the other side. Now, what is A on n? That's alpha n times n. So what do we get? We just get beta n alpha n times n. In other words, the same set of vectors are eigenvectors of the product A times B with eigenvalues which are just the products. But we can also see from this that it doesn't matter which order we multiply A and B. If they have a simultaneous set of eigenvectors, in other words, if there's a basis which are simultaneous eigenvectors of both operators, then it doesn't matter which order we multiply them, because in any order we're just going to get beta n times alpha n times n. The order that we multiply two ordinary numbers is immaterial. Alphas and betas are just numbers, and it doesn't matter if we write this as beta n alpha n or alpha n beta n. And from that we see that the order that we multiply A's and B's won't matter if they have a complete basis of common eigenvectors. All right, the necessary and sufficient conditions, I won't prove this, but the necessary, it's clearly a necessary condition, it's also sufficient, the necessary and sufficient conditions that there exists a basis of vectors which are common eigenvectors of both, simultaneous eigenvectors of both, are that A times B is equal to B times A. That's necessary and sufficient. Another way to write it is A times B minus B times A is equal to 0. Now remember, A's and B's are operators, they're not numbers in general. But if they're compatible, then it doesn't matter which way you multiply them. And the symbol for AB minus BA is called the commutator AB. The bracket, this is not a bra and a ket, the square bracket with A and B sandwiched inside it with a comma, that's by definition AB minus BA. So, with all of this little bit of notation, the necessary and sufficient condition for two operators to be compatible is that they commute, that their commutator is 0. This, of course, is not always true for every pair of operators, but when it's not true, they don't have a complete set of common eigenvectors, and they're not compatible. You can't, in general, measure both of them, or you can't know both of them simultaneously. What about position and momentum? Are they compatible? Well, from what I told you, it's clear that they're not. There are no common eigenvectors, none whatever. All right? So they can't be compatible. But we could check this by checking whether position and momentum commute. In other words, it should follow that position and momentum don't commute if there are no common eigenvectors. We can check that. We can just do the calculation of multiplying p times x and x times p and see if we get the same thing. So let's do that. And in the process, we'll find out exactly what xp minus px is. It is not 0. So let's work it out. Here's what we want to calculate. xp minus px. Now, if we, well, operators. Now remember what x does to a wave function. It just multiplies it by x. What does p do? Minus I h bar d by dx. So we can write this as x times minus I d by dx minus I d by dx times x. All I've done is substitute for p minus I d by dx. But what on earth does this mean? You're not allowed to just write d by dx. You have to, d by dx has to do something to a function. So let's take this and see what it does to a general arbitrary function. Let's try to figure out what this operator is by seeing what it does when it operates on a general function. So let's take this thing, x minus I d by dx minus, now we just minus times minus is plus, plus I d by dx times x, and apply it to a function of x, psi of x. Now it makes sense. Now it makes sense. The first term here is just x. Oh, what did I leave out? H bar. H bar. H bar multiplies the whole thing. Okay, H bar times the whole thing. X times minus I d by dx times psi of x. Remember, when you multiply operators, a, b, and you apply them to vectors, you first apply b, and then you take what you get and you apply a to it. Okay, so here it is. We first apply minus I d by dx to psi. Let's take these two terms and work them out separately. First of all, we get h bar, and then this term gives us x minus I d psi by dx. All I've done here is apply this d by dx to psi. The x is to the left, so it doesn't get differentiated. Only the psi gets differentiated, and then we multiply it by x. In the other term, we have plus I h bar, and now first we hit psi with x. That means we have x times psi of x, and then we differentiate the whole thing. What's the derivative of x times psi of x? We have to work that out. The derivative of x times psi of x has two terms. In one of them, the derivative hits x and leaves psi. In the other one, the derivative hits psi and leaves x. So just this piece of it here, I h bar, gives us dx by dx, that's 1 times psi of x, plus x d psi by dx. This is just differentiating the product x, the x psi. So there's an I h bar and another I h bar here. Let's see what we have. We have minus I h bar x d psi dx, and then we have plus I h bar x d psi by dx. They cancel. In other words, the term that you get when the derivative hits psi cancels this one here. So that cancels. We can just forget this and forget this. All that's left over when you do this operation is I h bar psi of x. So here's what we learned. We learned that xp, or just, xp minus px, when you think of it as an operator hitting any wave function, just multiplies the wave function by I h bar. In other words, this thing does exactly the same thing as multiplication by a simple number, a simple complex number I h bar. One writes this by saying that the commutator of x and p, xp minus px, is equivalent to, or is equal to, multiplication by the number I h bar. xp minus px is I h bar. Now, as a classical equation, that's nonsense. X times p is equal to p times x. But as an equation for operators, operators don't necessarily commute. The order in which you multiply them counts, just like matrix multiplication. What this is telling us is that x and p are operators which don't commute, and the worst possible situation, incidentally, is when their commutator on the right-hand side is just a number. That's as bad as any commutator can be, and it is the reason that there are no common eigenvectors at all. There are no common eigenvectors. If there was a common eigenvector, then at least if you were to put that common eigenvector here, then at least when it acts on that common eigenvector, you would get 0. But there are no common eigenvectors, and that's an indication of the fact that the commutator is just a number. It's as bad as it can be. Okay, let's stop for a minute, and yeah.
That seems that every vector is an eigenvector of the commutator.
Every vector is an eigenvector of the commutator. This is true. That is true. With its same eigenvalue. Yeah, true. Well, that just tells you there's no information in the commutator. I mean, the commutator is not an interesting observable. Every time you observe it, you get the same number. So, okay, so it's not, it doesn't tell you anything about the system. I'm talking about thinking of this as an observable. It doesn't tell you anything about the system when you measure it. xp minus px is always equal to I h bar. In classical physics, it's always equal to 0. This was Heisenberg's crazy equation, xp minus px is equal to I h bar, that people thought he had lost his marbles when he wrote it down. Maybe he did lose his marbles, but in any case, it's a correct equation.
Another question.
Yeah.
Going back to the way you define eigenvalues and eigenvectors.
Yeah.
It seems like x times any vector is just x times that vector, so why isn't our vector an eigenvector?
No, because x is not a number. Yeah. Okay. Here's what it would mean to be an eigenvector. You'll have some function, arbitrary function, and if you have an operator which operates on that function and gives you a multiple of that function, let's say 2 times that function, then it's just 2 times the same function. Okay? If the eigenvalue is I, then it gives you I times the same function. If you multiply this function by x, it doesn't give you the same function back, even a multiple of that function. It gives you a function which will look like this, because you're multiplying it by something bigger over here than you are over here. Okay? So for example, let's suppose this function were just e to the minus x squared. E to the minus x squared has a bell shape like that. That is not a numerical multiple of x times e to the minus x squared. Okay? The only eigenfunctions of x are delta functions, because when you multiply them by x, only one value of x gets picked out. So it is multiplication by a number for a delta function. Right. So it's not, every function is a multiple of every other function if you allow variation in the coefficient. When we say it's an eigenvector, we mean with a numerical constant coefficient here. Not an x, but a 3, or 3 plus 2i, or whatever. Okay, so that's, I knew that was going to come up. I was waiting for somebody to ask it. Thank you. Okay, so here's the setup again. We have 2 slits. Now, let's suppose we closed up one slit, and took a beam of particles coming through here, described by a wave function. The particles are described by a wave function, some psi of x, and the simplest thing would be to have a psi of x, which was just, for example, an e to the ipx. This would describe a particle with momentum p coming in from the left. Yeah, p over h bar. Right? The particle passes through the hole, and the probability wave, psi, spreads out like that. In fact, I could even write down what it is, but I don't want to write down what it is. We'll just draw a picture of it. All right? Now it hits a screen. And when it hits a screen, it's varying from here to here, from here to here. It's a wave. Then it has a trough and a high point, low point, high point, low point, and so forth. When it hits the screen, in the vertical direction here, we also see variation. We just see the variation of the wave radially imprinted on the screen as a variation along the screen. Now, if you think about it, even if these waves were uniformly separated, like so, they would not look quite uniformly separated on the vertical screen. Right? They would look more closely spaced up here than they do down here. Just try it out. Take a compass and a piece of paper, draw some concentric circles like that, and you'll see that they get more closely spaced up here than they are here. Right? If we were to approximate the wave vertically by an e to the I, let's call it p over h bar y, that wouldn't be such a good approximation because the wavelength varies as we move up and down. The wavelength is shorter up here than it is here. Right? All right, but let's just say over some interval, it looks pretty much like an e to the I py, like that. Some vertical variation along the y-axis here. This is the y-axis. Now let's open a second hole. Put the second hole over here. Oh, before we open the second hole, what is the probability of finding the particle at different values of y? Now this is only a good approximation for a small interval, but still, for that small interval, what's the probability for finding the particle at different y? It's uniform, because if I multiply this by its complex conjugate, I just get 1. All right, so the probability vertically over some small interval where the function can be approximated like this is uniform. The magnitude of e to the I p over h bar y is constant. All right. Now supposing we open a second hole. A second hole will also create a wave, similar kind of wave, which will add to the wave that comes out of here. So the wave that comes out of here will get added to by a second wave which comes out of here. What we're doing is we're taking some state described by e to the I py, and we're adding to it another state, something we never do in classical physics. We never add states in classical physics. But we're adding a second vector. This is a vector describing what happens if the particle goes through the first pinhole. If the particle goes through the second pinhole, it creates a different wave vertically here. And in fact, the different wave up in here has a slightly different variation. We could represent that by saying the second wave that comes out of here might look like e to the I q over h bar y over the same interval. Over the same interval, they have slightly different variation. Slightly different variation because they're at different heights vertically relative to the whole. So they have slightly different variation. Now supposing you took either one of these has a magnitude equal to 1. So if we only had one hole opened, vertically here over some range of distances, we would have a uniform probability distribution. A probability distribution which would not vary vertically. All right? No variation vertically in the probability distribution if we only opened one hole. It might vary slowly, but the oscillations implied in this function here would not cause any kind of oscillation in the probability because this thing squared, the oscillations go away, right? Okay. What if we take the sum of these two, which is what happens if we open both holes. Another way to say it is if we open hole number 1, we get out a wave function psi of x. We get a state of psi. Let's call it psi 1. If we open hole number 2, we get out psi 2. If we open both holes, the state of the electron, or whatever it is, becomes psi 1 plus psi 2. In other words, it becomes the vector sum of the two states that it started with, the two states from the individual holes. Okay, now let's ask what the probability to find different y is. All we have to do is take this and multiply by its complex conjugate. So let's do it. Let me call this, let's get rid of the h bar. Let's work in units where h bar is equal to 1. We get tired of writing it. So it's e to the I py plus e to the I qy, but then we have to multiply it by e to the minus I py plus e to the minus I qy. What have I done? I've taken the wave function and multiplied it by its complex conjugate. Okay? If I only had one of these, then the probability would be uniform along the y-axis, either one. But now I have both of them. Let's calculate this. E to the I py times e to the minus I py. What's that? 1. We also have e to the I qy times e to the minus I qy. That's also 1. So the terms e to the ip times e to the minus ip and e to the iq times e to the minus iq altogether give us 2. Then we get plus e to the I py, e to the minus I qy. That's coming from this term times the far term over here. And then we have plus e to the I qy times e to the minus I py. Or to write it slightly differently, this is twice e to the I p minus qy, 2 plus e to the minus I, or e to the I q minus py. What is this? E to the I times something plus e to the I times the negative of that. Twice cosine. Twice cosine. So this becomes twice 2 plus 2 cosine of p minus q y. 2 plus 2 cosine p minus q y, or even simpler, just twice 1 plus cosine of p minus q y. What does this do? Is this constant? No, it's not at all constant. It has a constant piece and it has an oscillating piece. The oscillating piece is just a cosine. The oscillating piece, there's one piece which is just 1. I'm forgetting the 2 here. There's one piece which is just 1, and there's another piece which is a cosine. Here's a cosine of something. We add them together where they enhance each other. They're twice as big. Where they cancel each other, where the 1 cancels the cosine, the answer is 0. In other words, there are places in this function where the answer is 0. Okay? In fact, what the sum of the two functions looks like is it looks like this. There are places where it goes to 0. What does that mean? That means if we open only one hole, the probability distribution is uniform. If we open the other hole, the probability distribution is uniform. If we open both holes, there are places where the probability is 0. Despite the fact that that particles could get here quite easily if we opened only one hole. So opening both holes makes it harder to get to this point here than opening either one of the holes. This is the puzzle, or the puzzling, not the puzzle, but the puzzling phenomenon of interference, and it's a particle phenomenon. In other words, it's a phenomenon that happens even if we only let one particle through at a time. One particle through at a time. If we open one hole, we get a constant probability distribution. If we open the other hole, we get a constant probability distribution. If we open both holes, we suddenly find that there are places where you can't get to. That's the significance of adding states, psi plus phi. Psi plus phi can have a complicated dependence even though the probability for psi and phi might be perfectly smooth. So interference, oh, notice how important complex numbers were here. Well, we've already discussed the importance of complex numbers in momentum, in having a momentum, e to the I p dot x. If we didn't have complex numbers, we could never have an eigenvector of minus I d by dx, obviously. Okay, questions. Let's stop for questions now. Yeah. Yeah, the bigger the distance between the slits, the closer the spacing, and the smaller the distance between the splits, the bigger the spacing. That's not, yes, that is correct. That is not what I wanted to point out here, though. I just wanted to point out that the phenomena of interference has to do with the ability to add state vectors, which is something you don't do in classical physics. But the answer is the closer the slits, the further the interference pattern, the bigger the interference pattern, the further the slits, the shorter the distance between the interference maxima. And we can work that out. We'll work that out another day. Yeah. Yeah, that's right. Yeah. Okay, so if you let a wave go through a hole, and you project it onto a screen over here, what you'll see oscillates. It oscillates pretty much like one of these e to the IPYs, but it oscillates with a changing oscillation. So for example, over here, let's just take, I'll draw it as an oscillation. Of course, it has a real and imaginary part, but the oscillation will have a longer wavelength over here than it does as you move out. The wavelength will get shorter as you move out. You know why? Okay, I'll tell you why. Anybody have an idea? I mean, you can just do it by calculus. You can take a wave going out like this and calculate how close the maxima are when they intersect. But there's a physics point of view also. How does the particle get over here? It gets over here by getting a kick in its momentum. So in order for it to get over here, it must have a larger vertical momentum than over here. Right at the center, it required no vertical momentum to get to here. To get to here down here, it required a somewhat bigger vertical momentum. Remember now, the bigger the momentum, the faster these functions oscillate. The bigger p, the faster the functions oscillate. So when you actually plot the function that you get from a wave going through a hole, you find out that pretty much anywhere it looks like an ordinary wave, except with a slowly varying, slowly modulated frequency, where the frequency gets a little bit, a little bit faster as you move away from the hole. Now you take the second hole and you open it over here. All right? At this point, in this region over here, the vertical frequency due to one hole is a little bit different than the vertical frequency due to the other hole because they're at different height here. Okay? So it's just like superposing, taking this wave and then superposing a replica of it, shifted. You'll be adding together two waves of slightly different frequency, just because from a single hole, the frequency varies as you move vertically. And that variation has to do with the fact that to bend, for the trajectory to bend, it has to pick up a vertical component of momentum. That extra vertical component of momentum makes it vary a little more rapidly down here. But you can work it out. I can tell you what the formula is. If a wave goes through a hole over here, and let's say that hole is at the vertical origin, then the wave that comes out looks something like e to the I p r. R is radial distance divided by r. R is radial distance here. Okay, now let's put the screen in here. What is the radial distance to a point at distance y? What's the radial distance from here to a point at y? Let's call this L. R is the square root of L squared plus y squared. And what's down here is not so important, square root of L squared plus y squared. Here you can see that what goes on here is not a simple plane wave e to the IPY, but e to the IP times a function which has a more complicated variation. If you take this function here, you'll find out that pretty much anywhere along here, it looks like an ordinary oscillation, but the oscillation gets a little bit faster as you go out here. Gets a little bit faster. For very large y, you can ignore L. And then it just looks like e to the IPY. Right? But in closer, the variation is a little bit different. And so what you're doing is you're putting together two functions with slightly different oscillation wavelengths. Well, of course, what we're doing here is calculating beats. These are nothing but beats. Two slightly different frequencies are, and now we're not talking about time, we're talking about vertical height. Two slightly different vertical frequencies are getting into phase, out of phase, into phase, out of phase, and creating this, this extra oscillation with a cosine here. That's all this is beats, but beats in the probability distribution. And it's coming because the wave that comes out, or the state of the electron that emerges from one hole here, is some psi, which is characterized by one wave function. If you open the other hole, you superpose a second wave function, which is characterized by a shifted wave function, and the sum of the two of them has this oscillation. But neither one of them has. Neither one of them has an oscillation in the probability. Together they have an oscillation.
Is that the Fraunhofer diffraction pattern?
What's that?
Fraunhofer diffraction pattern?
I don't know what Fraunhofer is. What is Fraunhofer? Remind me. I forget what Fraunhofer is. It's just a diffraction pattern. Yeah, it's just a it's a diffraction pattern. It's the diffraction pattern in this case of two holes. Right. Okay. Now, somebody asked me about the distance between the maxima. If the two holes are very close together, then you're adding functions which are almost identical. In that case, the p and the q here are almost the same. Okay? If the p and the q here are almost the same, it's like beating together two almost equal frequencies. All right? You get a very, very long wavelength. So if the two holes are close together, then this cosine here has a very long wavelength. If the two holes are far apart, then you're beating together two waves with somewhat different frequencies. And so you see a shorter wavelength for the, or a shorter interval between the maxima. Any other questions?
know,
Yes. One little,
you know, when you put the detector,
Say it again?
you put the detector there at the hole,
okay.
you can get to that one?
We certainly have not gotten to it yet, because in order to get to it, we have to talk about a composite system. The composite system now being the electron plus the detector, and talk about the concept of entanglement between the detector and the electron. Right. So what's being discussed here, which I'm not going to talk, well, I will talk about it, but I won't derive it now, because we have to understand how to combine systems together. At the moment, we're talking about a single electron, or we're talking about a sequence of experiments, each one involving a single electron. Supposing there was an object over here which detected which of the holes the electron went through. Now, by detecting which hole it goes through, it means the electron leaves an imprint on something. It leaves an imprint on some other system, telling that other system, I went through this hole or that hole. When that occurs, the interference pattern is destroyed, but we're not in a position yet to discuss that, because we have to discuss entanglement before we do. That, incidentally, was the subject of the previous lectures on quantum mechanics, and it is in there, but we'll try to discuss it a little bit again. Okay, so as I said, that's part of the problem of combining systems together, the systems being whatever it is that detects the electron and the electron. More complicated story. Wow.
When the particle deviates from the horizontal, you mentioned that it gets a vertical peak in momentum.
Wait, say it again now? Oh.
When the particle deviates from the horizontal,
Yeah.
it has to get a peak.
Well, in order for it to deviate from the horizontal, it must have picked up some component of y momentum. All right? If it picked up a component, some significant amount of y momentum, or another way to say it is if it doesn't deviate from the vertical, it must have meant that there was no y momentum. And in fact, that must mean in this location over here, the function is varying particularly slowly, which it is. All right? The slowest variation over here. In order for it to get out here, it must have gotten a kick. To get a kick, it now has a y component of momentum, and the y component of momentum means that it has a certain oscillation over here.
So where does the energy come from?
Oh, there's no energy to change the momentum. The energy is proportional to the square of the momentum, and the square of the momentum hasn't changed. It's roughly speaking like bouncing. Well, you have a target over here, a stationary target which doesn't move, and you bounce a ball off it. The ball changes direction, but there's no loss of energy.
So that means the x momentum would correspondingly decrease.
Yeah, exactly. That's right. The magnitude of the momentum is determined by the distance between these maxima and minima in the radial direction. That is just the original same spacing as the spacing that came in. Spacing that goes out is the same as the spacing that came in. So the wavelength coming in is the same as the wavelength going out, but it's converted into a spherical wave. But when projected onto the vertical axis, you see a variation in the frequency vertically. And that corresponds to having picked up some vertical momentum. And as you say, that would also imply that the horizontal component of momentum must be a little bit less up here than it is down here. That's a good point. No other question? Yes.
Yeah, so a question on the, so we have a wave function that's now hitting both poles, essentially. Right?
That's right. Wave function? Right.
So is it meaningless then to talk about a corpuscular particle going? I mean,
Well, we're sending through one particle at a time. Out of the electron gun, one particle at a time is coming through. One particle at a time doesn't make a wave-like pattern like that. It just makes a spot on the detector. But we do it many, many, many times, and we discover that there's a probability distribution on the detector here. So each event consists of a spot on the detector. It's only the accumulated effect of many spots on the detector that will create a pattern on here. And the pattern will be the pattern that looks like this. Notice one thing. This is always positive. Positive or zero is negative nowheres, cannot be negative. That's because we multiply the thing by its complex conjugate. So the probability distribution is never negative, but it does vary, and it varies in some places is equal to zero. Yes?
How does this compare to like the interference of light?
Well, the interference of light is a special case. Light consists of a large number of photons. Photons are particles. They satisfy the same rules as electrons. If we attenuate the beam of light, for example, by sending it through a series of filters which filter out almost all the light, then we'll find out that very few photons are coming through, and what we'll see is a flash, a flash, a flash, a flash, eventually building up to the pattern of the wave-like interference. If, on the other hand, we send a lot of light through all at once, well, then we'll just see the probability distribution as a pattern sort of created all at once. But that's just because a lot of particles came through all at the same time. So we see the particle aspects if we slow, not that we don't slow the particles, but we decrease the number so that they're coming through one at a time. Let's say 10 years between photons, and we see a blip every 10 years. Well, they come through randomly, but let's say on the average once every 10 years. Then we see a blip, but if we wait 1,000 years, then those 10 years per blips add up to an interference pattern. So as I said, we're not going to explain strange quantum phenomena, but this is the description of it. Yes?
I'm still having trouble with the one-hole experiment.
The one-hole.
And trying to understand where the oscillation comes from, the limited oscillation you see somehow.
Well, you don't see an oscillation from just one hole.
What do you see on the screen? Or what's the distribution of probabilities on the screen from one hole?
It's just a blob.
It is a blob.
Yeah.
Okay.
Right. All right. The question is, what does a wave function look like? So let me roughly write down what the wave function looks like. It looks like an E. Oh boy, I must remember to tell them to put fresh pens. Can that be seen? Not very well, I'm afraid. All right. Probably red is better than blue, I imagine. Let's try it. We're talking about one hole, right? One hole. So basically for one hole, you see some kind of e to the I times some function of x, which is not exactly x, px, but it's something like px, times another function, let's call it rho of x, where this is a rather smoothly varying thing. This is a slowly varying thing. Oh, I should call this y. Let's call this y. All right? So there's some oscillation multiplying something which is not oscillating very fast. Roughly speaking, it looks like e to the I px, p over h bar x, times some smooth function rho of x. Incidentally, p over h bar is likely to be a rather large number, which means that this oscillation is generally very fast. This rho of x is a smooth function which doesn't vary very much over the range here. Now what happens if we multiply this by its complex conjugate? If we multiply, and this is a real function, this is real. Here's where the imaginary parts come. If we multiply this by its complex conjugate, then this goes away and we just get rho of x squared. Okay? And rho of x squared is a nice smooth function, and we see no oscillations from one hole being opened up. Rho of y. Rho of y. I keep writing x, but I keep meaning y. Rho of y. Now, if we, and of course, as I said, this isn't exactly e to the I py. You can think of it as a slowly varying p as you vary up and down here. So there's a p which varies slowly as you move up and down here, times a nice smooth function. But then you open a second hole, and the second hole is some e to the I, let's call it p prime or q over h bar y times another smooth function, a second smooth function, rho of y, where the second smooth function might just be the first smooth function slightly displaced. Okay? Slightly displaced because you lowered the hole. Either one of these, if you were to square them, you would not see the oscillation. But when you add them together and square it, then you see the beats between these two things. So one by itself, you see no interference pattern. Yeah, okay, right. All right, it depends, well, you see something that depends on the details of the hole. Okay, now it's a good point, and let me just spell it out. If the hole has rather sharp edges, right, then what you see is a wave coming out of here, but you also see a wave that got produced right at the edge. The sharp edge created a little wave around the sharp edge, and the other sharp edge creates another wave around the sharp edge, and it's almost as if you had two holes. If the edge is not so sharp, if it's a kind of fuzzy hole, then it doesn't create an interference pattern. Then the interference pattern of the single hole is not there. It's true, a single hole can make an interference pattern by scattering off the different parts of the hole, and that's correct. Yeah, yeah, but it's quite distinct from this. It's different, right, right. Yeah, you see some circles, but the circles are different than the interference pattern that you see because of the two holes. Right. Mm-hmm.
So in the two-hole situation, shooting one electron through at a time, there are places on the screen that will never be hit.
That's right. The two holes are open.
Zeros are,
Yeah.
watch the spots forever, there'll never be any spots.
Yeah. Now, I mean, nothing is ever quite that good. I mean, there's a bit of an idealization here, but this is essentially correct. Yeah, there's dark spots, which can be very, very dark if you have good, tiny, tiny holes, and everything is very, very ideal. No cosmic rays, no noise in the room. Everything is as ideal as possible. Then you can see some pretty dark interference spots in there, and those dark interference spots are for in an idealized situation there would be no particles sitting there. Yeah.
Is there a difference if the two holes are not the same size?
As long as the two holes are small. If the two holes are small, then it really doesn't matter whether they're identical or not. If one hole is big and the other is small, then of course it'll make a difference. But yeah, small compared to the separation, right? And the wavelength. It's also important that everything, it's also important that everything be small or not too much bigger than the wavelength of the light. Yeah, I say electrons, but if you were to do this experiment in the laboratory, you'd want to use photons. Yeah. Photons have much longer wavelength. I mean, ordinary light has wavelength many, many times longer than the typical wavelengths that you can make for electrons. It's hard to make long wavelengths for electrons. But in principle, if you could create electrons with long wavelengths, you could do pretty much the same thing. Long wavelengths, what does long wavelength mean? It means very low momentum. Very low momentum means very slow. All right? How do you make very, very slow electrons? It's not so easy, because where do you get electrons from? You get electrons out of hot wires, for example. The hot wires eject the electron with some velocity. How do you get very, very, very slow electrons? Not so easy to get them. So if you want to make long wavelengths, you want very slow, and it's not so easy to get very slow.
So the slits are likely to be large compared to that.
What's that?
The slits are likely to be large compared to that.
For electrons, yes. You need to make the slits very, very small and very, very close together to see this. That is true. So even optically, you need to make the slits pretty close together. They're visibly close together. They're not so close together that you can't see them, but you need to make them close. Yeah.
Independent of the source, you change the source and you still get the same effect.
If you change, you get the same source, you see? Yeah, you get the same effect. Once the electron comes out of the hole here, it pretty much forgets what it was doing over here, and it just becomes an electron which was produced over here. It becomes an electron which was shot out from that point. That's the idealization, that you can approximate the electron as an electron ejected from exactly that point or exactly that point. Okay? An electron ejected from this point or from this point add up to a wave which has this kind of interference pattern. Yeah.
There's a way to bring the same electron back.
Say it again.
If there's a way to bring the same electron back, it still would get the same effect.
If there was a way to send the electron back.
No. Once it has gone out,
Yeah.
the same electron somehow could be cycled back through the hole.
Through the hole here.
Yeah.
Wants to recycle.
Certainly.
Wait, you want to cycle the electron through one hole and back through the other? No. You can do that.
From the screen.
The first issue of reversibility.
You want to know what would happen if the electron passed through and then you reversed everything? Is that what you're asking?
After you recorded it on the screen,
Yeah.
and that actual electron somehow could come back through.
Well, you could imagine that the electron bounces off the screen, leaves a little spot there and bounces off, and then you could, of course, you could then try to focus that electron back through the hole. You could do that. And you would get the same kind of pattern on this side.
I think he wants like a cyclotron.
No, you want a cyclotron? No. I don't think you want a cyclotron. You can use the same electron over and over. You can use the same electron over and over. You can collect the electron from here, bring it around, bring it through the hole, whatever you want, and do the experiment over again with the same electron. Oh yeah, you can definitely. You can use another electron, or you can use the same electron.
The last time you told us that if you detect it, then that changes it. If you don't detect it,
If you detect it over here, that changes it. Yeah. Oh no, if you detect it at the hole. Okay. Let's come back to now you're asking the question about reversibility. That's a different question than whether you can use the same electron over and over for the same experiment. Okay. All right. Let me come to that next time. In fact, let me come to that after we talk about Hamiltonians. We have to understand Hamiltonians and evolution before we can answer that question. Yeah.
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.